For the last 2 days, 3 periods-ish, we have been looking at galvanic or voltaic cells and how the differences in reduction potentials is the driving force for electrons to be conducted through a system. Okay? And the bigger the difference between the reduction potentials, the bigger the voltage, right? The larger the voltage. Okay? So energy was produced by that potential difference. Okay? Aaron, because he uses his cell phone all day and takes advantage of that potential difference, has to do what? A few times a day. What's that?
Well, it's once, but it's not even a day. It's a night.
But anyway, what do you have to do? You have to charge it up. Which is what does that do? Why do you charge it up?
To refill it with electrical potential energy.
There you go. To get the energy back. So in the first, to discharge it, to use it all day, he's using the energy that had been in or stored in that battery in a chemical form, chemical energy, okay? And at some point during the day, a few times, he has to get that energy back into there, okay? Which is all that is the reverse process, okay? In which case we're going to use this idea, he's then using the idea, his battery now became an electrolytic cell, meaning the reverse process is going to happen. Energy is going to have to be put back into to get everything separated again. Okay? So, moving on. Electrolytic cells. Electrolysis is the application of electric current to a chemical system, basically trying to restore the imbalance that had already been there. As it says, it uses electrical energy to cause a non-spontaneous, or the better phrase is thermodynamically unfavorable reaction to occur. Mr. Lehman's room. Okay, she's probably not going to like this. Yeah, well, because we're, finishing up a chapter, but I'll let her know. Okay. Yep. See ya. You're going to go down to the guidance. Yeah. Was I right?
Well, what? Yeah,
that you're not going to like this?
I'm more for that in order.
Anyway. Uses electrical energy to cause a thermodynamically unfavorable reaction to occur. So basically we're converting electrical energy to chemical energy, whereas in a galvanic cell we're using chemical energy and we're converting it to electrical energy. It's just that whole energy transformation things that you guys learned way back and whenever you took physical science. Okay? These are already set up at equilibrium. We talked about the other day, it might have been yesterday, it might have been 2 days ago, that a galvanic cell will continue to operate until it reaches equilibrium. Okay, and then there's no driving force. We run out of one of the components, and therefore we no longer have the ability to get those electrons to be generated. Whereas an electrolytic cell, it's just the opposite. It's at equilibrium, and we drive it away from equilibrium. There's a lot of different terminology that you may not have been exposed to yet. I don't know. I know we offer like 3 different physics courses now, so I don't know at what point in time you guys get into electricity or when, if ever. Max, help me out here. No electricity in physics for you? You're just starting? Okay. And you, yes, no? Are you two in the same class? I probably shouldn't have asked you that. Anyone else? No. Okay. What about... Oh, okay. Anyway. So here we go. An ampere, which uses the abbreviation capital A to represent... All an ampere is a unit of electric current. here's where it gets a little confusing. I'm going to give you an analogy here, okay? I'm going to use something that you're incredibly familiar with. What does the D stand for? Distance. Okay, you guys all get that, okay? What are some units for distance that you're aware of? You're fired. Meters, centimeters, kilometers, blah, 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 blah. Those all have their own little abbreviations, right? Well, electric current uses the symbol I, capital I, and electric current is measured in amperes. Now, interestingly enough, notice we said meters, centimeters, kilometers for the distance thing, right? You can have milliamps, you can have megaamps. You see where I'm going with that? Okay. So the current is I, but the unit for the number of electrons is the amp. Okay. Sometimes students get confused with those two things. I just wanted to make it a little bit more, hopefully, available to you. And as it just says, the ampere is the flow of electrons. It's measured in coulombs per second. I have a note here. Does anybody have a book opened up? I don't know why I have the note. It might just be showing you the... Yeah, it's just showing. Okay, forget it. Now, therefore, I equals Q. Did we talk about Q yet? And this is the first time this has come up? Okay. Q over T. Yeah, and Q equals charge. So, how do I want to say that? Yep. And that's in coulombs. And T, of course, is time. And that's in seconds. If we're talking about I, we're talking amount of charge per second. Coulombs per second. An ampere is a measure of the number of electrons. So up in part A, where it says the flow of electrons, okay, it's measured in coulombs per second. So that's all an ampere is. Amps is a measure of the number of electrons. Okay? Here's a couple, oh, go ahead.
Is there like an equation that relates them?
Yeah, right there.
So I is it an A?
No. She just... All right, you just did what I said that most students do. I is current, just like D is distance. Distance can be measured in meters, centimeters, kilometers. Current, I, is measured in amps, milliamps, megaamps, amps. Do you see the similarity? And the reason, and this is, listen, first of all, there's 8 other people in the room thinking the same thing you are. They all thank you. 2, the reason you're having trouble with this is because this is brand new. You've never done this before, right? But you've done distance measured on all these different units before, so you're comfortable with that. You'll get there. A couple of interesting points here. You guys always see, I'm sure, have seen these signs before that have said danger, high voltage, and that kind of stuff before, right? Stay away, high voltage. Has anyone ever been shocked by a doorknob before? Yeah, it's an incredible amount of voltage right there. You guys okay? Has anyone ever been zapped by a Tesla coil? or a Van de Graaff generator. Huge amount of voltage there. How are you guys doing? Yeah, you're okay, right? So it's not the voltage that's the issue. What is voltage? It's potential difference. The greater the difference in electrical potential between McKenna and I, the more chance that electrons are going to go from one place to the other. If there's a really large potential difference, those electrons will just leave one of us and go to the other one without a means of getting there. Without a conductor like a wire or something. Okay, that's what happens when you get shocked. The potential difference between the two objects is enough, the electric potential difference between the two objects is enough that the electrons are just going to jump that gap. Okay, and which is why, with a doorknob, you have to actually get fairly close to it, right? And how many of you did I use the Tesla coil with? Just a couple of you? Okay, but most of the rest of you saw that happen, right? You don't even remember. Okay, so anyway, you had to get pretty close to it. I mean, you were, within a few centimeters anyway for that to work. I might have to do it here. Anyway, but it was a huge potential difference. I mean, there has to be a large potential difference for electrons to actually jump a gap. So it's not the voltage that's the problem, it's the current that's the problem, the number of electrons. You could actually stick what's the voltage on a electrical outlet? Does anybody know?
No, it's like...
Voltage. Go ahead, Max.
12?
Oh, no, that's like a car battery.
Oh.
120.
Oh.
You guys know this, 110 to 120, or in the U.S.'s system of electric generation, it's 110 to 120. Europe, it's a little bit different, but that's okay. Has anybody ever gone to Europe and had to get an adapter for your devices? Yeah. Because they just use a different voltage for their standard. Anyway, to get shocked by, like, say, a doorknob, we're talking about 10,000 volts or so. I mean, a very, very large number. But you're okay if you get shocked by a doorknob. How many of you have, other than Aaron, how many of you have ever stuck your finger in an outlet before? That's hilarious. Have you? Are you okay? Well, no, sorry about that. We already know the answer. Wait, Sydney, you did?
Willis has a really bad outlet, and I touched one, and it shocked me really good.
Okay. That also explains some things. But anyway, no, but see, so why, so if it's, I know that. And that also explains some things, doesn't it? When did you do that?
Probably, I know it was like a big event, it was probably in 8th grade or something like that, and it didn't have the plate.
Okay. And what happened? Did it hurt? A little bit. Paul?
Yeah,
So now the stories are starting to come out. Keep going.
The school that Albert and I worked at, it was really bad. I went into the pump room one day without shoes, and when you turn on the bill, it shocked me so bad that I shook like it's like a cartoon, and my arm, I couldn't really lift it for the next hour.
Okay, so far Paul is providing the best example of what I'm talking about.
One time my brother told me to touch a fence, and it turns out it was an electric fence. And you grab it, and nothing happens at first. So you sound like your fence, and the next thing you know, it's up your arm and up your neck, and it was bad.
So here's the thing. This is at 110 to 120 volts, okay? Voltage is relatively low, rather than getting shocked by either the Van de Graaff generator or the Tesla coil or just getting a shock from a doorknob, okay, which is thousands of volts. So what's the difference? And again, it's not the voltage that's the problem, it's the number of electrons, the current that's the problem. When you put your finger in an outlet, you have an unlimited number of electrons. It's never going to stop. Because the power plant's like, yes! I got a place for these electrons to go. Seriously, it's an unlimited source of electrons. It's more than happy to provide that opportunity to go through you, even though the voltage isn't that. So it's the current that does the damage. I'm just saying, it's kind of interesting to me. You always see the high voltage. Now, where are you seeing those high voltage signs? We're at a power plant where there's an unlimited source of electrons. but still, yeah, so it's the current that causes the problem. That's one other thing that you guys have been exposed to in your lives that may never have thought about why this is true before. How many of you, at some point in time in your lives, have ever been confused by that? How many of you have ever been confused by that and wanted to know which one was which? Okay, right, because there's that O thing. Is it on or is it off? Now you know. I know what I'm telling, now you know. What does the I stand for? Yes, but on the switch, what does the I stand for? On, because it's providing electric current. The O stands for off. I get that, but now you know. The I means on because it means that there's electric current going through it. No, this is even more fun. This is even more fun. What if there's only one button? It's both of them together. I'm just saying. These.
Whoa, okay.
Yes, you have. What kind of computer do you have? Oh, you haven't seen that before?
Shock vac. You know what I'm talking about?
I don't have one. I'm trying to think of something that I have here that. Yeah, but it doesn't have the I and the O. Or the, yeah. Anyway, Sydney, yes, you have. You're just not thinking about it right now. No, it's not. No, it's got it done. All right, so anyway, the things you learn in AP Chemistry. Moving on. So, as we already know, in part 2 there, voltage. We use a capital over V to represent voltage. We already talked about that that's potential difference, which is joules per coulomb. So, I erased my I. Okay. A coulomb, as we already know, is an amount of electric charge. We talked about that the other day. And lastly, we have Faraday's constant. Now, I've seen a lot of different tables, a lot of different textbooks. It's hard to represent that F. Let me see your book. Oh, you're way back. Nope, too far. There it is. Yeah, okay. I have seen, you guys ever see those really fancy script calligraphy Fs that are like italicized and loops and things all over the place? That's a Faraday, okay? Your book, nicely enough, and the AP on there, does anybody have the AP equation sheet available to them? They have gotten away from using that really fancy, we have one over here. Yeah, they've gotten away from using the really fancy one now. All they're using now is a capital, uppercase, italicized F. So an uppercase, italicized F. and your book does that, my notes do that, the AP thing does that. I'm just telling you, don't get your panties in a bunch if you see this really fancy capital F. It's the Faraday, okay? And we're going to use that a lot. The AP equation sheet, you've put that away, I believe has rounded this lately to the value that I'm giving you there, the 96,500. Again, don't get your pennies in a bunch if you see a source that has 96,485. Is that what's on there? Mm-hmm. Okay, so the equation sheet for the AP exam is giving the 96,485. That's what you would use on the AP exam. Don't use a 96,500. Okay? Anyway, moving on. Use what they provide, I guess is what I'm saying. So anyway, that's in coulombs per mole of electrons. So the Faraday is 96,485 coulombs per mole of electrons. Where I'm going with this is, for the first time, we've looked at the number of electrons. Way back, it was just a couple weeks ago when we were doing the redox the balancing redox equations. We were using the number of electrons that were being transferred as our way to balance the equation. Okay, and I said there's going to be times when you're going to need to know that number of electrons. This is that time. Okay. Not only did we use that transfer of electrons to help us balance the equation, but it's also going to be used in our electrolysis calculations here. So really, all I'm doing with this stuff is, the reason I'm emphasizing all this stuff is essentially we're going to use various combinations of these things to calculate the number of electrons that need to recharge a battery, if you want to look at it that way, or do something called electroplating. Now, electroplating, a lot of things that you guys use in your lives are electroplated. Your bumpers on your car, some of the bumpers, anybody have a chrome bumper? Yeah, nobody has cars anymore that have chrome bumpers. That's a good thing. You guys know what I'm talking about. You've seen these before. This is chromed, okay? So basically it's either like, in this case, probably a brass pipe, maybe a copper pipe or something like that. Your bumpers on your cars, if you still have one that has a chrome bumper, which is essentially steel with this stuff plated on the top of it. Anyway, all you have to do is put this object that you want to have this coating on it in a solution, running electric current through that solution, and the same idea where we talked about the copper ions plating out on the surface of the electrode when we were talking about the galvanic cell, the same thing kind of happens, okay? Except it's more of a permanent idea where you can silver plate something. You can, what are some other things you guys know of that are plated? Okay, like a gold plate, like yeah, some jewelry. It might be like a piece of zinc or something. Who knows? You know, like a cheap metal that has a gold surface that's plated on the outside of it. Yeah. Well, yeah, and that would be a good example. Yeah, a penny's like 95% zinc. I mean, there's just a really thin coating of copper on the outside. Does anybody remember that little coating of copper, the penny that I used to have? It went away in the move. I don't know what happened to it. We took all the zinc out of it. Do you remember that at all? It was like paper. Yeah, so I'd pass around this penny to people, and it was like paper. I mean, if you threw it up in the air, it fluttered down. There's that little copper in a penny.
Olympic gold medals are gold plated.
Yeah. So anyway, that's what you do is you can use this electrolysis concept to plate out one metal onto another metal. Okay? So a lot of the questions we're going to be dealing with are going to be how much time is it going to take to do this, how many electrons are going to be needed. These are the types of questions we're going to be looking at. I'm going to walk through a couple of examples with you. you're going to be relatively highly successful on this stuff. You really will, because you guys are really good at math, and it's just a matter of taking some equations, some constants, and plugging and chugging is all it is. The hard part becomes when you're given an AP question is this in a galvanic cell or is this a electrolytic cell? You have to make that determination, okay? And remember, a galvanic cell, you start off with two, you're started off you're far away from equilibrium, and you're using that to create some electrical energy, whereas in an electrolytic cell, you're already at equilibrium, and you need to add energy to the system, some electrical energy to the system to get whatever it is that you want to happen. Let's look at example number 1. It says calculate the mass, in this case, calculate the mass of aluminum that is produced in 1 hour by the electrolysis of molten aluminum chloride if the electric current is 10.0 amps. All right, so let's walk and talk through this one. What information do we have available to us? I'm going to leave that there. Okay, well, we know the current. It's 10.0 amps. The time is 1 hour. And we're looking for mass of aluminum. Okay, how can I get there? Well, I'm looking for mass of aluminum. As I'm looking at these pieces of information that I have available to me, and these are all, by the way, these are all on your equation sheet. I would highly recommend having that equation sheet available to you so you can kind of get used to learning how to access that. Do you see anything here that I can use to get to mass of aluminum? Jason says yes. What would that be? What piece of that? Okay, right there. If we knew the moles of aluminum, we could get to the mass, because we know that. We know how to do that, right? So clearly, we're going to use Faraday's constant at some point in time. Well, in order to use Faraday's constant to get to moles, I'm going to need, I can use the charge. Okay? Because, remember, a coulomb, or a Q represents the amount of charge in coulombs, so therefore, this equation can be rearranged such that I can solve for Q. And please don't let that be a motivation to you. Oh, thank you, McKenna. See, McKenna is really about the only one that ever gets my jokes first. Thank you for that, McKenna. I was anticipating you getting it first. You get them, but she gets them really fast usually. I said, please don't let this be a motivation. Q-I-T. Kind of looks like quit. Okay, well, anyway, so we can use the current because we know the time, right? We know the time. We know the current. We can now find the number of coulombs. We can find the charge, okay? And using Faraday's constant, which has coulombs in it, we can get to moles, just using that as a conversion factor. So what we could do is say, all right, there are 10.00 or 10.0 amps. Of course, we're going to have to convert our hours to seconds. You guys probably already know that. 3,600, yep. So 3,600 seconds. And then all we have to do is use looks like which is going to give us what, by the way? That's going to give us coulombs, okay? So now we just have to use the 96,458 coulombs per mole of electrons. Here's the hard, what's that? Oh, my bad. I don't know what I was doing. Apparently got a little dyslexic at some point in time. Must have gotten zapped by some electricity somewhere. Now here's the key. How many electrons were transferred? Oh, good try. But that's good, okay? We're going from aluminum chloride to aluminum plus three. So in the transfer, there are 3 moles of electrons for every 1 mole of aluminum. Would you guys agree? Do you see where I'm going with that? Okay, so for aluminum, and let's go back to your redox days a week ago, to go from, oh, sorry about that, my bad. It's It's already at a 3+. My fault on that. Aaron was thinking it. As an ionic compound, it's already at a 3+. We're making solid aluminum. Okay, the metal. So how many electrons are going to be needed to convert this to that? 3.
Okay, I got it.
You better now? That was my bad. I led you astray a little bit there. Okay, so anyway, so really what we're doing is reducing the aluminum, right? So for the aluminum ion to go to the aluminum metal, we're going to have to add 3 electrons, if you want to look at it that way. Okay? So anyway, 3 moles of electrons per mole of aluminum, and then all we have to do is convert that moles of aluminum to grams. And there you go. So all we're essentially doing is using the various combinations, and again, all of these little relationships are clearly shown on your equation sheets, and I believe they're all in the same group there, aren't they? Well, sort of. Boom. Yeah, it's all there. So if you look on your equation sheets that you're provided, there is a part that says bottom left-hand corner, thermochemistry and electrochemistry. At the very bottom of that sheet, you have the I equals Q over T. For those of you that actually have access to this, can you guys see that? Okay? If you look over to the right where they define all of the variables and what they are and if there's any constants they give them, directly across from the I equals Q over T, you'll see Faraday's constant. You'll see 1 volt equals 1 joule per coulomb. They'll give you time, they give you Q, they give you I. I mean, everything's right over there. All right. Any questions before we go any further? You tell me. Jacob, would you concur with that? Do you have any idea what her question was? Yes. Okay. And the reason you know that, Sydney, is because, remember, this represents a coulomb here. Cancel. Moles of electrons cancel. Moles of aluminum cancel. It's dimensional analysis. That's all this is. Okay. What I want to do on number 2 is, I don't know if you guys have noticed the way I like to usually do things, I usually walk through one with you, or I'll do one for you, and then next I have you tell me what to do, and then I cut you loose on your own. Now, those of you that know what the heck you're doing, go. I think there's 4 examples. For those of you that would like to play around with this some more, tell me what to do. So, looking at example number 2. Ooh, they cheated. I'm sorry. I even gave you the number of electrons. That doesn't happen very often. Tell me where to start. Unless you guys want to be cut loose, I'll cut you loose. I don't care. Looks like everybody wants to be cut loose. Awesome. How much time do I have? Does anybody know? 5? Oh, that's plenty of time to get the...
Is that the Tesla coil? Yeah. I'll do it again. Okay. Have you ever had a joy buzzer? That's a joy buzzer. So weird. I feel something. Anybody? There we go. You've never done it before? But you've done the buzzer drop. Oh, really? Okay, go ahead. Look, she says Alex will smile. This is what happens every time. Anybody? Valerie, just stop. What you doing on your break? You got it. On your break? No, I can't use my phone. What did you do on your break? Valerie, it's just like a vibration. You look straight. It's a really, here, let me have a really big shot. No. No. No one else? What would that do? Okay, apparently no one died, so... Yeah, let's try it. Come here. You have to. Wait, but it's not a complete circuit, so it won't do anything? Not if you hold the wood. Jason!
It doesn't hurt.
I was so happy that he was holding on to the metal. I was just so... Come here. You have to... Get up.
Stand.
You stand the entire study hall, yet when I want you to actually stand and do something. Oh, touch the metal there. What happened? You're the one who stuck your finger in a socket. Want it again? Look, more. You'll be like Frank. That was the first time you threw it in the vegetable. Brittany? No? Caleb.
I didn't quite remember, but I said that. Did you just enjoy the divided 2 instead of a 3? Yeah, because...
See, now you gotta do it.
I got like 30.
Oh, look at you, he's on big time. You gotta get your...
I'm so short. Okay, so this makes sense.
It is a usually what I'll do is I'll get like 3 or 4 people to hold their hands.
So,
Yeah, so it might be this, it might be this
I thought
first
you were
round
gone.
by the time.
No, I was not. Well, like gone.
Alright.
So,
Valerie?
No.
You're gonna laugh. You're gonna go ow and laugh at the same time.
Valerie, you're fine. I'm scared. I want to. Okay, I'll do it. Whatever. Okay. So,
Do it.
What do I do? Just
Finger. got it.
Oh my god! What the? Oh, that feels weird.
Yeah, right. That's why when Aaron first pulled the pencil, I was like,
Spooky. Yeah, that feels crazy.
not only did she laugh, she screamed.
Wow.
Oh.
We're probably only like a minute left. I'm probably not going to have enough time to get those up there. So, it's similar. You're just solving for a different variable. Right. We'll look at the rest of those tomorrow.